2212. Starting with the introduction, the description or purpose of the lab, using the physical principles of conservation of energy in order to predict the behavior of circuits containing different resistors and capacitors, observing said behavior through the use of an online model, and using multimeters to measure values of current and potential differences in an ideal circuit. Some fundamental concepts of conservation of energy and charge, Kirchhoff's circuit laws, steady state currents, Ohm's laws, resistors, capacitors in series and parallel, capacitance, time dependence on resistor capacitor circuit. The results of the lab. The actual values of current and voltage given in the model match those predicted by formulas. In an RC circuit, the magnitude of current is time dependent based on exponential equations. The model used, using an online ideal model of a circuit in order to observe the behaviors of resistors and capacitors in different combinations. Some assumptions: the resistance of wires is negligible, the resistance of ammeters negligible, and EMF equals delta V capac plus delta V resistors. Continuing to experiment and observations, the system was a circuit, the surroundings were everything else. In part 1, a circuit with two 1.5 volt batteries and two resistors and two ammeters were wired into a circuit. Some of the predictions was that I1 would equal I2, REQ was found to be 147 ohms, and the current in the circuit was found to be 0.020 amps. The actual reading turned out to be the same thing. When we replaced one ammeter with a voltmeter, the readings of potential difference was 3 volts and current was 0 amps. In the open circuit, no current potential difference across opening equals that across the power source. Closed circuit and measure potential difference across each segment was this next part right here. Down below you can see all the calculated values of each segment. All the potential differences of the segments. When they were added up, they were found to be 0 volts. This follows the loop rule, saying that the round-trip potential is 0 volts. Current was 0.02 amps as expected. The ammeter reader doesn't change because voltmeter has very high resistance, meaning basically no current flows through it, and the path of the current in the circuit remains essentially unaltered. This next slide, you can see a graph graphing potential difference versus the position in the circuit that we're at. As you can see, at each point there where there's a battery, potential difference increases, and each time there's a resistor, it decreases, with the slope of the 100 ohm resistor being a lot steeper than that of the 47 ohm one. When you connect the ammeter in parallel with the 100 ohm resistor, current reading increases to 0.06 amps, which is less current comes into contact with the 100 ohm resistor since it splits at the node, and since the ammeter has 0 ohms of resistance, the effective resistance of this portion of the circuit decreases, ultimately increasing since I equals V over R. Resistance of 47 ohm capacitor was found to be 48 ohms, and the resistance of the 1000 ohm resistor, was 102 ohms. The resistance of the wire was 0 ohms, and the resistance of the ammeter was 0 ohms. This is higher than expected due to low precision of the ammeter. For part 2, a 10 ohm bulb, 20 ohm bulb, 9 volt battery, and 200 millifarad capacitor were put in a circuit. The battery connected to the 10 ohm bulb and capacitor in series. The bulb starts bright, then decreases down until going out, which is charging. Current decreases from maximum down to 0. When you disconnect the battery, the bulb once again lights up, then decreases until going out. This is discharging. Current decreases from maximum down to 0. For the 10 ohm bulb, 10.5 seconds of charging and 12.4 seconds of discharging was measured, and for the 20 ohm bulb, 17.3 seconds of charging and 22.3 seconds of discharging was found. In this next slide, a couple of readings across the capacitor were taken as a function of time using the equation above, and then eventually the natural log version shown below that one. This was linearized into the plot seen below. For a 9 volt battery, 200 millifarad capacitor, and 30 ohm light bulb, this is all calculated. The experimental, using the slope of this graph, an experimental RC value was found to be 6 seconds, which is the same as the expected one. For discussions, model discrepancy, likely none since I used an ideal computer model of a circuit in order to collect the data. Sources of error, because I used an ideal model of a circuit, the only source of error was likely human error with my found times for charging and discharging, likely not entirely accurate due to human error and stopping the stopwatch. For discussion questions, what if you were doing this live in real life and used an actual ammeter instead of an ideal simulated ammeter? What's different about a real ammeter, and how would it affect the circuits you hooked it up to? If you did this live with real circuit components, accessing the virtual circuit to see if you could determine how to behave differently from the real ammeter used. What if you were doing this in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? If you are completing this lab with real circuit components using an ammeter to measure how long it takes to charge the capacitor to connect directly from the battery to the ammeter.